I'm going to talk here for a minute about Lewis structures, okay, Lewis symbols. This is a picture here of Gilbert and Lewis, and if you ever go over to Berkeley, UC Berkeley, you're going to see a hall there called Lewis Hall. He spent most of his time, most of his career over at UC Berkeley. Now the objectives we have here, we want to go through and develop the shortcut symbol, that's called the Lewis symbol, and we really are interested in the valence electrons because they're the ones that do most of the interacting when we're making bonds. We want to make a distinction between the ground state and the bonding state, and we'll see that. We'd like to talk about bonding capacity, introduce the idea that when you make a bond, a covalent bond, that lowers the potential energy of the system. And we want to realize that sometimes where you draw those dots makes a difference, and a lot of times it doesn't make a difference. And last, we want to just really demonstrate how do we draw these Lewis dot symbols. Now we have a little chart that we were using earlier, and so we can see, well, just going way back, so sodium, go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we can go back and do this for all these different atoms. And this is no big surprise. Now there's actually more to this chart, I just couldn't fit it on the page, and that's okay. Now, the part we really care about are the valence electrons. So we really care about this outer electrons here, in this case the n equals 3 level. The other electrons, these are all kind of buried, so we're going to call that the noble gas core, the neon core in this case, and they don't really get involved in the bonding. Now if we will go back and just kind of copy these electrons out here in this outer shell, then we could see that we'd have a picture like that. And for magnesium we'd have 2, and for aluminum we have 3 valence electrons. Silicon we have 4, and phosphorus we have 5. Well, in another talk we're going to talk about the fact that, that if you have some half-filled orbitals, you can make a bond. So in this case here, we can say we can make one bond because we have one half-filled orbital, and here we couldn't make any bonds. Here we could make 1, here we could make 2, and here we could make 3. That's called our bonding capacity. And every time we make a bond, we actually get some energy back. We lower the energy of our system. So making bonds is a good thing. Now, because it is a good thing, you can see what happens is that if we were to take like one of these electrons and actually split them up, then we could make 2 bonds instead of 0. Now in this case over here, it's not going to do us any good to move that electron around. We're still going to make 1 bond no matter where we put it. But here, in our third family, again, we could split those up, move that electron over, and now we could make 3 bonds instead of 1. In this case, we could make 4 bonds instead of 2. And again, in our last case, it doesn't matter where we double up those electrons, it's not going to help us to make any more bonds. So 3 is all we can get. So for this family, and this family, families 2, 3, and 4, then if we move an electron, because if we have a full orbital and some empty orbitals, if we separate those electrons, we can actually make more bonds. So this kind of picture here, that's what we want. If we say, what's the ground state? What's the lowest energy state that any of these atoms could have? And if an atom has no chance of making a bond, then these would be the best ways for their electrons to be in the orbitals. But if there is a chance to make a bond, then these are the best ways for the electrons to be arranged. So we could call that the bonding state. And if we are going to do pictures, these symbols, then the bonding state would probably be the best way to do this. But let's go back a little bit and say if somebody says draw the ground state electron configuration ground state symbol, then we say, okay, here we have one side that has 1 electron, and we have 3 sides that have no electrons, and so we leave 3 sides blank. There are 4 valence orbitals, and each of the sides could represent one of these pairs of electrons. So for this magnesium, we could put 2 on one side and blank, blank, blank. For aluminum, we could put 2 on one side and 1 on one of the other sides. For silicon, we could have 2 on one side, and then we could go 1 on one side, 1 on another side. And finally over here for phosphorus, 2 on one side, 1, 1, and 1. Now here comes the idea about whether it makes a difference. Now if, let's say for aluminum, I could have put 2 on one side and 1 on the other side, 1 on the opposite side, that's fine. It doesn't matter where we put those. Now I've been starting by putting my 2 electrons on the right hand side of each symbol, and that makes no difference. It's just when we start making molecules, you're going to put those wherever it's a convenient thing. So again, this whole idea, I'm going to clear all this off. Okay, the idea is that if we are talking about the lowest energy state, which is the ground state, I misspelled that. The ground state. And if we had a question, it would very clearly say, draw the ground state symbol. Then for, let's say, magnesium, we put the 2 on the same side. For aluminum, 2 and a 1. For silicon, maybe 2, 1, and 1. Now for phosphorus, it doesn't matter whether it's ground state or not, because you get the same picture. Same thing for sodium. It doesn't matter which side we put it on. This is going to be the same for ground state or bonding state. So it only makes a big difference in families 2, 3, and 4. And the reason they make a difference is they have a full orbital and they have an empty orbital. So they have a full orbital and they have a place to put the electron if we decide to separate them. Now, most of the time when we do this, we are going to do it with the idea that you are going to make a bond. So let's start right in the middle. So carbon, we know, has 4 valence electrons. So the Lewis symbol for carbon is we would separate those 4 and go 1, 1, 1, 1, put 1 on each side. Now nitrogen, we have 5. So we're going to say 1, 2, 3, 4, and 5. We start doubling them up. For oxygen, okay, 1, 2, 3, 4, 5, 6. So one way to do this is just to start on one side and count up your electrons and put 1 on each side, then start to double them up. When we get to neon, we have 8 valence electrons, and we draw it like that. Now going back, for boron only has 3 valence electrons, so we'd start on one side and put 3 around. Beryllium, we only have 2, and here's a place where I say, that we're going to find out that electrons, because they're negative, they're going to repel each other. In beryllium compounds, we're actually going to get a 180-degree bond angle. So when we make bonds, it's actually going to look like this. And it's going to be 180 degrees. So we might as well learn how to put those on opposite sides right now. And lithium, only 1 valence electron, doesn't matter which side you put it on. Now if we could do the other family, the other period, let's say right below, we can see silicon. There's really not a lot of choices, 1 on each side. For nitrogen, okay, we could again start on any side we want to, so long as one side has 2, the other sides have 1. For sulfur, you can kind of see that what's going to happen sometimes is you can say, well, why don't I put 2 opposite to each other and 2 singles, so double, 2, 1, 2, 1 instead of 2, 2, 1, 1. These are identical. They look different because these are 2-dimensional pictures, but in reality, an oxygen, let's say like a water molecule, is actually a bent molecule, but you might look at it from the side, in which case it would look like this. So we can say, okay, maybe those 2 electrons are next to each other like this, or maybe they're opposite to each other like this. It's really just the idea that you're looking at a 3-dimensional object in a 2-dimensional flat piece of paper. So they're actually the same thing. Going back here to chlorine, okay, we put one on each side. And again, 3 sides need to have 2. And where you leave the other one is up to you. Now, argon will look the same either way. Now, let's go back to aluminum. And again, we could put it on any of the 3 sides. Magnesium, again, I would put them opposite. And sodium, again, you can put it on any of the 3 sides. Now, back here in hydrogen. Hydrogen we know is only going to have 1 valence electron because it only has 1 electron. But helium, we have to remember that helium is 2 electrons in the 1s orbital. So, they're only actually going to have 2 electrons, and they should be written together because they are together in the same orbital. So that one kind of is a little bit different. I have to remember that. So going back over our objectives, we developed a shortcut symbol, that's the Lewis symbol, using dots. We make a distinction between the ground state and the bonding state. So ground state is putting the electrons in filling the S first and then doing the P's if the atom has no chance of making a bond. But almost all the time we draw that according to the bonding state. And we'd say just put 1 on each side before you double them up. Bonding capacity, half-filled orbitals can make bonds. Full orbitals, empty orbitals don't make bonds until a little bit later. We can introduce the idea that when you make a bond, that lowers the potential energy. And what that really means is making the bonds is a good thing for molecules. And the position makes a difference sometimes. Okay, other times it doesn't. So a situation like magnesium, we would like to put them opposite to each other because it really does come out to be a 180-degree bond angle. But other times it makes no difference, like around the water. For oxygen, do you want to put 2 and 2, 1 and 1, or 2, 1, 2, 1? Either way is fine. And we got to demonstrate some Lewis symbols. Gilbert Lewis, okay, he did a lot of different things. You know, he worked on covalent bonds. He also worked on thermodynamics. He was the one to coin the term photon. Spent all his time over at UC Berkeley. He was actually nominated for the Nobel Prize 35 times, but he never got it. Now we're going to be using his idea, his symbols, the little dots, okay, the Lewis symbols, and when we do molecules for the rest of this chapter, it makes a really nice shortcut way of showing bonds.